moving on to current electricity now. In other words, when the charges move. Right, so we're doing circuits, and you'd have some familiarity with circuits from junior cert, but we want to get our kind of head clear on the model that we are using from day one, and we follow the model. Okay, so basically, you know that's a power supply. Now a power supply, power is energy per unit time. We know that, so it's an energy supply. So it supplies energy to the charges. We're not worried what the charges are, whether they're electrons or not. Our model, they're just charges, and we always talk about positive charges going from positive to negative. Okay, and the long part of the battery here is the plus, and that's the minus. You don't need to put in the plus and the minus. That's what that indicates. And then you basically have a circuit. Let's take this circuit. Okay, you know that's a resistor, and let's say there's a bulb here. Okay, and let's say there's a switch here. Okay, if the switch is closed, the circuit is complete. Okay, and charges can flow from positive to negative, and that's the model we're using. Charges flowing from positive to negative. They require energy to move. Okay, so if we had no power supply, the charge would be there would not be moving, and they would have no current. Remember, current is the flow of charge, or charge divided by time. Okay, remember we looked at that briefly in lesson 4. Okay, charge divided by time. Okay, so that's it. Now remember from lesson 4 as well that the potential difference is the work done per unit charge. Okay, so it's the work done in moving the charge. So it's the energy used. So anytime we talk about voltage, now voltage is a general term for potential difference or for EMF. Okay, so it gets a bit confusing, but it shouldn't be. Voltage is just a general, kind of a nickname. Okay, EMF, you'll come across E. That's the total voltage in the circuit, all the energy. So effectively, usually, it's the energy being supplied by the power supply. So if it's a 6-volt battery, EMF is 6 volts. It's the total voltage. And then that EMF is used in different parts of the circuit to push the charges through resistances. Okay, so in this case, this would have a resistance, and this would also have a resistance. It would take a certain voltage to get it through here, and a certain to get through here. So remember, anytime you talk about voltage, you're thinking of energy. How much energy is needed, okay, and we'll have a look at that in a second with potential dividers. But that's the idea, okay, that's the plan. If something has a high resistance, it takes a lot of energy to get through. If something has a low resistance, it takes little. Think of high resistance, a muddy field, a low resistance, a grand dry field, and you're trying to get through the field, okay, right? So that's what you're thinking of, okay? So that's our model, okay? You'll see a nice example of kind of an analogy with the model in the cartoon guide to physics, the 4 pages that you're going to be reading after this article, after this lesson, okay, or during this lesson, but after this bit of it. Okay, so we're going to look now at 2 things regarding resistors, a potential divider and a potentiometer, and we'll see how these operate. Okay, so I'm going to show you on the board first, and then we're going to see it practically. Okay, so if we take this situation, okay, so let's say that this is 6 volts. Okay, so the EMF is 6 volts. Okay, the total energy available is 6 joules per coulomb. So the total energy available is effectively 6 volts. Okay, with 2 resistors. Now let's say this is a resistance of 2 ohms, and this is a resistance of 2 ohms. Effectively, you would expect that it has 6 volts available. This is the way it works. So 6 volts available. It would need half of the energy to get through this one and half to get through this one, because they both have the same resistance. So if I connected something between here and here to measure the voltage, which we call a voltmeter, okay, right, and if I connected another one between here and here to measure the voltage, you'd expect those 2 voltages to be the same, okay, both be 3 volts. So we've divided the 6 volts into 3 and 3. This is why it's called a potential divider, potential difference divided into 3 and 3. But let's say if we change this, and let's say we make this a 10 ohm and this a 20 ohm. Well, no, just think about this. It's kind of ratios, okay? It won't get complicated. Okay, which do you need more resistance? You need more resistance for this one. Or sorry, you need more energy for that one because it has more resistance. In fact, you need twice as much energy. So you have 6 volts available to you, and you need twice as much energy. You can look at it in terms of ratios. The ratio is 10 to 20, or 1 is to 2. So the ratio has to be, the ratio 2 is to 1. Usually you can do these, you can think these through. So what's it going to be? 4 volts be required for this, 2 volts. So the reading on this will be 2 volts, and the reading on this will be 4 volts. And that's how a potential divider works. A potential divider is very nice, except the problem is, of course, if you wanted a voltage of 1.75 volts, you'd have to find two resistors that would work for that resistance, with that ratio, and that can be quite difficult. So this is the kind of the theoretical one, the potential divider, and then we move into one where we can actually get these ratios working easier, and it's called a potentiometer. So let's look how we operate that. Okay, just watch carefully because it's just the same thing effectively. Okay, what we effectively have, okay, is instead of having the two resistors separate, okay, we just use one long resistor like that. Okay, but we have a connection in the middle, a sliding contact here in the middle, and that sliding contact can be moved back and forth. If it's right in the middle, the resistance on the left and the right is the same. If it's over here 1/6 the way along, well, there'll be a 1:5 ratio and so on. And we call this a potentiometer then, instead of a potential divider. Okay, so we can check again with our voltage here. Okay, and the other voltage should be here. So effectively, and we'll look at this in our notes in a minute, effectively that's the same thing. That's the same thing as we did earlier. But the glory of this is, let's say these add up to 6, at the moment it's 3 and 3. If I move this to 1/3 of the way along here, this now is 2 to 4, okay, and so on. So I can reduce or increase the voltage here. And that's why it's called, this is a fancy potential divider. So you can get any voltage from 0 to 6 here. And that's what we'll be using then, okay. So that's your potentiometer. That's what we'll be using in experiments. We won't be bothered with this bit, okay. And this here, which we can change from 0 to 6, will be effectively the power supply for the experiment, and the experiment will take place down here, as we'll see. Okay, but that's not for today. Okay, so we're going to look at it in action now in room 4C on tour. Okay, and then we'll have a look at it in the notes as well, and our job will be done. Okay, sorry, you'll read 4 pages of the cartoon guide to physics, and your job will be done for day 1 of current electricity. Thanks a minute.